Every year, thousands of tons of fiberglass rebar are produced worldwide, a material that's throwing down the gauntlet to steel. Imagine hundreds of spools of fiberglass, thinner than a human hair, merging into a single river, passing through sticky resin baths, red-hot dyes, and scorching ovens to be born as a rod that's 4 times lighter than steel, twice as strong, and completely immune to rust. This rebar is capable of doubling the lifespan of concrete structures and changing cities forever. But the most interesting part is hidden in the very heart of this process. If you watch until the end, you'll discover a secret that will completely change your understanding of the future of construction. It all begins at one end of a massive workshop, where a structure resembling a giant library for threads stands. This is called a creel. On a wall several yards high, hundreds, and sometimes even thousands, of huge bobbins are installed in neat rows. On each of them is wound the finest glass thread, or roving. This isn't the kind of glass that windows are made of. This is a special fiberglass, produced by melting glass and drawing it through microscopic holes. The result is threads thinner than a human hair, but with incredible tensile strength. These will be our skeleton, our internal army that will give the rod its insane strength. From each of these hundreds of spools, its own separate thread is drawn, and they all come together into one thick, fluffy strand. It's like thousands of small streams merging into one large river. This dry, white strand is the soul of the future rebar. Next, this river of fiberglass begins its journey. It passes through a system of guides and tensioning devices. This is a very important, though inconspicuous, stage. Every one of the thousands of threads must be tensioned with the same force. If one thread sags, while another is too tight, the load in the final product will be distributed unevenly, and it will lose its strength. Therefore, the machine carefully aligns them, preparing them for the most important moment: a baptism in resin. The dry glass strand is slowly submerged into a bath filled with a thick, sticky liquid, similar to honey or syrup. This is a polymer resin, our meat that will grow on the glass skeleton. It's a complex chemical cocktail. The base is usually a polyester, vinyl ester, or epoxy resin. A hardener is added to it, a catalyst that will trigger a chemical reaction and force the liquid to turn into a solid plastic. Various additives can also be added here. Pigments to add color, ultraviolet inhibitors so the rebar isn't afraid of sunlight, and flame retardants for fire resistance. The task of this bath is to saturate every single, even the tiniest fiber. The strand must be completely submerged in this resin so that no dry spots remain. The saturated strand, heavy with sticky resin, exits the bath and heads to its point of birth, the forming die. This is the heart of the whole process. Imagine a thick steel plate with a perfectly round polished hole, the diameter of which exactly matches the diameter of the future rod. The die is heated to a certain temperature. When the wet strand is pulled into this hole, several things happen at once. First, the die, like a press, squeezes out all the excess resin, leaving only the necessary amount. Second, it tightly compresses all the fiberglass strands together, forming a perfectly round rod. Third, the heat from the die initiates the initial stage of the chemical hardening reaction, or polymerization. The resin begins to transform from a liquid into a gel. At the exit of the die, we can already see the familiar shape of the rod, but it is still soft and vulnerable. But how does it get its famous ribbed surface to hold well in concrete? Immediately after exiting the die, while the rod is still hot and soft, a special strand of the same fiberglass is wound around it. A thin, resin-saturated thread is wound in a spiral on the surface of the rod, creating a relief pattern. Sometimes, for even better adhesion, fine quartz sand is sprinkled onto the sticky surface, which adheres permanently to the resin. Now, our rebar has not only strength, but also teeth with which it will hold onto the concrete. The formed and wrapped rod enters the longest part of the machine, the curing tunnel, or polymerization oven. This is a long chamber that can extend for tens of feet, inside which a high temperature is maintained usually 400 degrees Fahrenheit. Here, the final transformation takes place. This is not just drying. Under the influence of heat, the resin molecules begin to actively bond with each other, forming a strong, rigid three-dimensional network. The liquid, sticky syrup turns into an extremely strong and hard composite material that permanently binds millions of glass fibers into a single monolith. It's like baking a pie. As the rod slowly moves through this hot tunnel, it acquires its final, rock-solid hardness. But what pulls it through this entire long journey, from the spools to the oven? At the end of the line stands a special pulling device, which gives the whole process its name. Usually, it's two caterpillar-like mechanisms, similar to tank tracks, located one above the other. They gently but very firmly clamp the already finished hard rod with their rubber pads and pull it towards themselves at a constant, precisely calibrated speed. It is they that create the force that pulls the fiberglass through the resin bath, through the forming die, and through the oven. The speed of this movement is one of the most important parameters that controls the quality of the final product. And so, from the other end of this long conveyor, an endless, perfectly straight, hard and hot fiberglass rod emerges. The final cord is cutting. An automatic saw is installed across the line. It synchronizes with the speed of the rod's movement, at the right moment makes a quick forward motion, and with a sharp zzzt, cuts a piece of standard length, for example 20 or 40 feet, from the endless ribbon. Then it returns to its starting position, waiting for the next section to arrive. The finished, still warm rods roll onto a cooling table, and then they are collected into bundles, tied, and sent to the warehouse. And just like that, before our eyes, thousands of fragile glass threads and a barrel of sticky liquid, having passed through baths, presses, and ovens, have turned into a lightweight, but incredibly strong building material of the future, ready to challenge rust and time in the concrete jungle. The fiberglass rebar market is not yet a giant like the steel market, but it's the coolest and most audacious newcomer at the party, rapidly gaining popularity. The global market for this material is already valued at hundreds of millions of dollars, and the forecasts are just insane. It's expected to grow by 10 or 12% annually. This means that more and more engineers and architects are looking at rusting steel and saying, "Dude, we can do better." And now for the main features that make steel rebar nervously smoke in the corner. The first and most obvious is weight. Fiberglass rebar is about 4 times lighter than steel of the same diameter. Sound boring? Now imagine this in real life. Imagine a truck carrying rebar to a construction site. It can bring 4 times more length of fiberglass rebar in one trip than steel because it's limited by weight. Or for the same amount, it will take 4 times fewer trips, which saves fuel and time. On the site itself, 2 workers can easily carry whole coils or bundles of fiberglass rods, whereas moving steel requires a crane. This is a colossal saving in logistics and labor. Second is strength. And here, fiberglass just steps into the ring and knocks out steel in the first round. Its tensile strength is about twice as high as that of standard steel rebar. So you understand, to break a fiberglass rod, you need to apply twice as much effort as for a steel one of the same diameter. This means that in some structures, rebar of a smaller diameter can be used, saving even more weight and volume. It's like comparing a regular rope with a climbing rope. At a smaller thickness, it can withstand much greater loads. But the main trump card, the real superpower of fiberglass, is its war against rust. The main enemy of any reinforced concrete structure, from bridges to parking garages, is not the load. It's rust. Water and salts penetrate through micro cracks in the concrete, reach the steel rebar, and it begins to rust. The rust expands in volume and literally tears the concrete apart from the inside. Annually, the US spends billions of dollars on repairing bridges, parking garages, embankments, and tunnels destroyed by rebar corrosion. And fiberglass? It just laughs in the face of rust. It is chemically inert. It is completely indifferent to water, salt, acids, and alkalis. This means that the service life of the structure increases dramatically. A concrete structure reinforced with steel is designed for more than 50 years. and a structure with fiberglass rebar is easily designed for more than 100 years. Every year, billions of square feet of drywall are produced worldwide. In the United States alone, over 27 billion. That's enough to lay a 3-foot wide path from the Earth to the Moon, and still have enough for halfway back. Imagine millions of tons of stone being transformed into the smooth walls of our homes. But the real secret begins where ordinary gray stone becomes a thirsty powder, a material that can miraculously turn back into stone. Watch closely. At the end, you will discover a secret that most people have never even guessed. The numbers behind drywall production in the United States are not just big, they are astronomical, and they tell a story of how the country builds, renovates, and breathes. In a recent year, factories in the US produced approximately 27 billion square feet of drywall panels. This number is so colossal that it's hard to comprehend. Try to imagine. If you were to lay out all this amount of drywall, you could create a continuous 3-foot wide path that would stretch from the Earth to the Moon and almost halfway back. Or, with this number of sheets, you could completely cover the entire territory of the state of Delaware twice, and still have some left over. This endless stream of building material is not only a physical product, but also a powerful economic indicator. The market for these panels in the US is valued in the tens of billions of dollars, reflecting not just the cost of the material itself, but also thousands of jobs in mines and factories, in logistics and construction. It all begins not in a workshop, but much earlier, in a quarry where gypsum is mined. This is a natural mineral, a stone that formed millions of years ago from ancient seas. It can be white, grayish, sometimes with pink veins. Huge excavators dig into the gypsum deposits and load dump trucks with boulders of this stone. These trucks bring tons of gypsum to the factory and dump it onto the raw material yard, creating entire mountains waiting for their transformation. The first stage inside the factory is coarse crushing. The gypsum boulders fall into the giant steel jaws of a primary crusher. With a deafening roar and grinding, the machine breaks the large stones into smaller pieces, the size of a fist. This is just the beginning. Then this crushed gypsum is fed by a conveyor belt to secondary mills. Here, dozens of steel hammers, rotating at an insane speed, break these pieces into even smaller fractions, turning them into something like coarse gravel. But even this is not enough. The final stage of grinding turns the gypsum into a fine, powder-like dust. It becomes so fine that it resembles flour or dust. This powder is the main raw material, but it still hides a secret that needs to be revealed. The next step is one of the most important and interesting. It's a process called calcination, and in essence, it's the controlled drying of gypsum. The thing is, in the crystalline structure of natural gypsum, water molecules are locked in. For drywall to be able to harden, this water must be temporarily driven out. To do this, the white powder is fed into a huge, slowly rotating kiln. It looks like a giant drum, tilted at a slight angle. Inside this kiln, a very precise temperature is maintained, around 300 degrees Fahrenheit. The gypsum powder, slowly tumbling inside the drum, heats up, and the water bound to it turns into steam and evaporates. Chemically speaking, gypsum turns into calcium sulfate hemihydrate, but to put it simply, it becomes thirsty. Now this powder, which is now called plaster of Paris or stucco, has a unique property. If you add water to it again, it will greedily absorb it and turn back into a hard gypsum stone. It is this property that lies at the heart of the entire production process. The resulting hot powder is cooled and stored in giant silos, resembling towers, from where it will be fed to the main production line. And now the most spectacular part begins, the creation of the sheet itself. In the workshop, there is a huge conveyor, hundreds of feet long. At its beginning stand two giant rolls of special dense paper, or paperboard. One roll is for the face side. It is perfectly smooth and white. The other is for the back side. It can be a bit darker and grayish. The ribbon from the bottom roll, the face side, is unwound and laid on the conveyor, forming an endless track. In parallel with this, in a giant mixer resembling an industrial food processor, the core is prepared. Our thirsty gypsum powder, water, and a whole cocktail of various additives are continuously fed into it. Each additive plays its own role. Foaming agents make the gypsum mass lighter and more porous, like whipped cream, to reduce the weight of the sheet. Plasticizers make the mixture more fluid, so it spreads evenly. Accelerators or retarders allow engineers to perfectly control the time it takes for the gypsum to set. Starch helps the gypsum core to better adhere to the paper covering, and fiberglass adds strength. This mixture, called a slurry, resembles a thick grey porridge. It is poured in a continuous stream directly onto the paper ribbon, moving on the conveyor. Special devices evenly distribute this mass across the entire width of the paper. The edges of the bottom sheet of paper are neatly folded upwards, forming the sides of the future sheet. And at this moment, the second ribbon of paper from the back roll is laid on top, like a lid. The result is an endless, perfectly even sandwich. Paper, gypsum mass, paper. This sandwich immediately passes between two rollers or under a forming plate, which compress it to a precisely specified thickness, for example, ½ an inch. The newly formed, still soft and wet sheet of drywall continues its journey on a very long conveyor, which is called the setting line. Its length can reach several hundred feet. As the sheet slowly moves, a real miracle happens inside it. The gypsum powder reacts with water. The rehydration reaction takes place. The gypsum turns back into a hard stone, releasing heat in the process. If you touch the sheet at this stage, it will be warm. In a few minutes, the loose mass becomes hard enough to hold its shape. At the end of this long line stands a flying knife. This is a huge blade that moves in sync with the belt, and at the right moment makes a quick, precise cut, slicing the endless sandwich into sheets of standard length, for example, 8 or 12 feet. This happens so quickly that the conveyor doesn't stop for a second. The cut sheets are now hard, but still very wet. They contain excess water that did not take part in the chemical reaction. It needs to be removed. Therefore, a special device flips the sheets and feeds them into the most large-scale structure in the factory, a multi-level drying kiln. This is a giant labyrinth consisting of several levels, each of which is a conveyor. The drywall sheets slowly move along these levels back and forth, traveling a path of several hundred feet inside this huge furnace. Hot air circulating inside gently evaporates the excess moisture from them. The temperature here is controlled very carefully. Only the free water needs to be removed without damaging the crystal structure of the gypsum itself. This process can take about an hour. At the exit of the dryer, the product we are familiar with appears, a perfectly dry, light, and strong sheet of drywall. But this is not the end. The final stage is finishing. 2 finished sheets are stacked face to face. Their edges are perfectly trimmed to be even and clean. A paper tape with information about the manufacturer and product type is glued to the ends. After this, robotic manipulators with superhuman precision and grace lift the finished sheets and stack them in perfectly even piles on pallets. Each stack is wrapped in protective film, labeled, and sent to the warehouse. From there, it will travel to construction sites to become part of someone's home, having transformed from a simple gray stone mined from the earth into a smooth and cozy wall. Drywall production is like a barometer of the construction industry's health. When the economy is on the rise, people actively build new houses and renovate old ones, and the demand for drywall skyrockets. The factories that produce this product operate at full capacity, and the flow of trucks delivering the finished sheets across the country becomes endless. The heart of this production beats in unison with the rhythm of the real estate market. Geographically, this industry also has its centers. Although drywall manufacturing plants are located throughout the country to be closer to large construction markets, the mining of the main raw material, gypsum, is concentrated in certain states. The leaders here are states like Texas, Oklahoma, Kansas, Nevada, and Iowa.